Hey everybody. Hey Chuck. Tech Talk Tuesday. Third season. Third episode. Episode number 107. Hey Charlie. Good job, man. Appreciate you checking in. Harry. Daryl. Daniel. Thank you guys. Got some allergies working on my nose today, so if my nose is red and I'm sniffling, I'm not sick. I just got allergies, man. It's crazy here. Hey, Chris and Daryl and Brian. Good to see you guys, man. Jamie Keeler. Hey, Joe, I got some interesting stuff I want to share with you guys today. Let's see if I can be presentable on the TV here. Let's try it one time just to see what happens. If I'm looking too terrible, I might have to go back the other way. Hey, how you guys? Got me a little slanted over here. All right. Hey, good to see you guys. Scott, Donald, Michael, Josh, how y'all doing? Oh man, it's a happy Tuesday here, nice and hot. Bryce, Corley, still got the coolest name, Tanner, Theodore. Hey man, thank y'all for watching. I appreciate you guys coming on here every Tuesday, 6 o'clock. Isn't that crazy, y'all? I just was looking how much stuff has changed in our life. Yours and mine in 107 weeks. It's amazing how much we've done and changed, and lived in Georgia and was building engines for a living and racing pretty good, and then we moved to Tennessee and started working on camshaft design in the last 107 weeks. Did camshaft design for a long time, but never really thought about selling them. I always thought that it would be cool for us just to have our secret just on us, so we could win all those NHRA races and all the different races because we had our engine advantages. But it never really crossed my mind because every time we would build one, I wanted the next one better. And we even bought a CNC machine, a 5-axis, to port and polish heads one time. Hey, Ronnie, PJ, Todd, Lloyd, we bought a CNC machine at one time so we could port heads. But Ron Reese was working at the shop 35 years and he was porting heads. So whenever we would find one that was pretty fast, we would spend a lot of money and time to digitize it and try and come up with a shape and a size that we wanted. And then by the time we got the digitization done, the post-processing, and created the surfaces and built a model to turn into a tool path to where we could make the fixtures and then build a head to match the one that we were doing, guess what happened? It wasn't good enough. Our learning curve has just been going like this. And so after about 10 years of trying to make a port and copy it and duplicate it, we decided, hey, Yaska and James, we came up with this really great idea to sell it and keep innovating and coming up with new ideas. Now, the guys that are doing the CNC stuff for a living, they've got some really cool machines. They've got some talented machinists, and they got the guys that know how to write all that stuff. Hey, Ronnie. Hey, James. And yeah, you're right, Brian. They were obsolete. So what we learned is as we continued to develop and reinvent the wheel, so to speak, we created some files that were just base stuff. So yeah, we could start right now with a Pro Stock Suzuki port, but we would definitely have to make changes to it. So then you go in and hey, Drew, Steven, you go in and you get a guy that's really good on the laptop or on the computer to go in and make all the little changes. But man, you could hand it off to Ron. He'd go in there and then he'd measure it. We would CC it, flow it, digitize it, and then we could cross-section it. The coolest thing wasn't copying it on a CNC machine in my world, in my life, was to get the digitized model where we could actually 3D model it and cut it in pieces and look at cross-sections and look at the shape and size of each section of the port was way more important to me because that showed us where, hey, Mark, good, thank you for signing up. And, you guys, if you watch, you'll see so many CNC ports now, just like my really great friend Mitch Brown. He does the monster cylinder heads for the Suzuki GS 1100 1150s, and it's a great piece. But one of his options that he has that we sell, because I actually own the file, but one of the options is a Pro Stock NHRA port. And that is a totally different piece. Mitch makes the Monster Head, which goes 390s on the Pro Mods. It goes 620s on the turbos in the quarter. Makes tons of horsepower. We use it all the way from school bikes all the way up through top gas bikes and pro stock motorcycles. But when we got done trying to make the most power we could, we needed a really, really big port to move so that at 13, 14,000 RPM, the restriction would be low enough that we could get in there and do some really good camshaft work, piston work, ring seal, and some trapping where we could grab the amount of air that cylinder head could flow and turn it into some usable cylinder pressure. Hey, Greg. So going back to not just watching me and looking at this stuff. Oh, yeah, let's look at the socks. Yes, I am. I can't see if you see it. It says officially retired. And I am sitting on the floor in Indian style. I guess that's what it is. And it's August of 2021. And let's go to some notes. And let's break down each one of these. I came up with this idea that I wanted to do ratios. And I know there's some people on here that are really, really smart. There's some really high knowledge, really way up there, people that know a lot. And I have mentors, just like you have mentors. And my mentors have mentors because we don't know the smartest guy. And the smartest guy is the guy that learned a lot from books and experience. And I call myself an engineer, but I'm a field engineer, which means I learned my craft in the field. I didn't do it in school. So you could say that, for instance, the 4 years we were with Team Winston, R.J. Reynolds Tobacco Company, the 4 years we were sponsored by them was definitely Motorsports University for me. And I did get a good degree there because I learned a full circle of what professional racing was, how to go fast, how to win, how to sell it, what they were looking for, how to give return on investment, and how to have enough pieces and parts and personnel to pull it off. And the main thing I learned that I can share with you, and it fits everything in my world today, is do what you say you're going to do. If you're going to mess around and really meant to say I'm going to try really hard, or if I have time or I really want to, is a lot different than I am. Because I am means no matter what, yes, you are. So that's my tip for that deal. Hey, Al, going back to these, I wrote down some ratios that are important to me. And if you're an advanced engine guy, if you'll listen to me just for the next few minutes, I will promise you that there will be something that has on this list that I will expand on each one of these subjects to where you'll say, I hadn't thought of that in a long time. I already knew that, but man, I really appreciate going back to the basics on it. And if you're a newbie or someone that has read all of these on the internet and you hear your engine builders talk about these all the time, these might be of interest to you. Air-fuel ratio, compression ratio, rod ratio, rocker ratio, bore-stroke ratio. I know what the BS ratio is. Yes, I see it on the internet every day, and it doesn't stand for bore and stroke, but that's the BS I'm going to talk about today. Intake to exhaust ratio, that's size and flow. The nitrous to fuel ratio. Gear ratio is something really cool. And then this down at the bottom, this is the star racing ratio. Not really. It's star racing GA. That's where Jackie catalogs all of these episodes that I do live, and she saves them and puts them in the Star Racing GA YouTube channel. So if you ever go and say, man, I wished I'd have got 105 or number 62 or whatever on these Tech Talk Tuesdays. Tech Talk Tuesday, number 107. You can find the episodes here. Thanks to Jackie and Julie saving those episodes, doing them up. Okay, so I'm going to expand on the air-fuel ratio for a minute. I want to tell you that the air-fuel ratio is what our industry talks about of how much air versus fuel we have. That's why it's called air over fuel ratio. So what it is if 13 to 1 air fuel ratio is good ratio. And this is confusing because hey David, hey Brian, Steve, Alan, yeah, rod ratio. I'm going to tell you what it is. Don't like prejudge me on this stuff now. But look, every one of these things, I'm getting ready to spend a few minutes on each one of these based on what I think I know, not what you know, and not what the guy that wrote the book knows, not Smokey or Grumpy, which were great mentors and leaders in our industry. But I got to tell you a couple things that have changed about some of this stuff. Not the math, but what we need and what we use today. All right. Hey, Jim, Damon. Okay. And look, let's enjoy this, okay? This is funny. I'm not having an argument or a contest with any of my smart heroes on here. I know there's some guys really smart. But anyway, let's say 13-to-1 air fuel is the number you're looking for, or your engine builder's target number is. That's 13 pounds of air to 1 pound of fuel. And if he's at 14-to-1, at full throttle, wide open, that might be too lean. And at, say, 11-to-1 pounds of air to 1 pound of fuel, that's going to be too much fuel for an amount of air, so it's going to be what they call rich. So you have rich and lean. And the power that the amount of air-fuel ratio you need for best power is somewhere around 13-to-1. There are guys on here watching that love 12.5-to-1 based on gasoline. Let me predicate that. And then if you're going to go for mileage, you need 14.7, 15-to-1, light load, light throttle, and cruising. Turn that fuel way down. If you've ever flown an airplane, and I know one of my friends on here is a good pilot, and when I learned to fly, they had a fuel knob that was sticking out the dash, and you'd be flying along, and they'd say, okay, now lean it out. And you'd watch the EGT meter, which was engine gas, exhaust gas temperature, and it would start getting hotter and hotter and hotter and hotter, and you'd be leaning that knob out, turning the fuel away, and it would go, I'd say, okay, now back it back out a half a turn, and then the EGT would go back down. That was tuning based on exhaust gas temperature. Nowadays, we have wideband lambdas that tell us how much oxygen and how much unburnt fuel is left based on a sensor, 6-wire sensor, that we use to tell us our air-fuel ratios. And that's another whole 30-minute episode that we're not going to do today. But I wanted to throw in, when I said 13-to-1 for full power on gasoline, or 14.7-to-1 at part throttle, low load gasoline, I want to tell you a little bit about, and I don't know anything about nitromethane other than it will blow you up. And I love watching the nitro cars, Top Fuel, Funny Car, Brittany Force, John Force, all those cool people that go out there and ride those bombs. The Nitro Harley guys, they riding bombs. But this is what I'm going to tell you, just a little bit of opinions on it, okay? Nitromethane weighs about 9.8 pounds per gallon. And Brittany Force won in Topeka, and they burn probably 13, 14 gallons of fuel in a run. But from the time they leave the starting line till the time they pull the parachute, they burn about 11 gallons of nitromethane, which is about 107 pounds of fuel comes out of that car. So that car is changing its weight from the starting line to the finish line dramatically because it's burning so much nitromethane. Also, the air-fuel ratio for nitromethane is around 1-to-1. You want to run 1 pound of air to 1 pound of fuel. And please take my generalizations, you guys, generalizations, and let's just consider the source, just this country boy from Georgia, talking about 13 pounds of air to 1 pound of fuel, gasoline, and 1 pound of air and 1 pound of nitromethane is 1-to-1 air fuel. Now, methanol might be 6-to-1. Gasoline might be 13-to-1. Nitro is around 1-to-1. I'm just letting you know that we need a lot more fuel to make that work. Okay, that was the big meat and potatoes. Compression ratio. Last week, I drew out some graphs for you on compression ratios, and I made a couple of mistakes. I said that if you had 1,000 cc's and you shoved it all in a 100 cc chamber, it would be 10-to-1. It's actually, I forgot to add the chamber volume of 100 cc's, so it would be closer to 11-to-1 air fuel closer to 11-to-1 compression ratio. Now, these numbers are, isn't it funny that we can make 12-to-1 air fuel on the dyno with a 12-to-1 compression ratio, and it'll run good, and then we get confused because those numbers are so similar, but they have nothing to do with each other. Air fuel ratio is the fuel to air. Compression ratio is how much the piston, when it goes down from the top to the bottom, it pulls in this many cubic inches, and then the chamber at the top is we shove that whole cubic inches up into that small area, and that gives us the compression ratio of the swept volume of the engine. Swept volume is bore and stroke, bore and stroke. And when it's time to compress it, we have it in a chamber. And if you have a pop-up piston, or you have a plus 7 cc piston, and you have a 100 cc chamber, that means you have shoved 7 more cc's into that chamber. So now your chamber volume is 7 cc's smaller than it was with a flat top. Another story, another day. Compression ratios. Today, most motorcycles and cars are over 10-to-1 on gasoline. Diesels actually run a lot of compression. You can get some really cool high horsepower sport bikes now, 1,000 cc's and whatnot, that have 11 or 12-to-1 compression ratio. And because all these are ratios, and I have some ones that are famous in my life, air fuel, compression, rod ratio, and rock arm ratio, I might say the wrong thing, so just listen up for me. And hey, Rusty, Rich, and Sean, bear with me, because I'm flopping around through here like a fish out of water. Compression ratio is how much the cylinder sweeps shoved into the chamber. People say, well, why wouldn't you run the most compression ratio you can? Well, gasoline, your fuel, has to be able to suppress the detonation that comes from the overheating. When you take 1,000 cc's of fuel and air molecules and you shove them into a 100 cc area, the molecules get so excited and they rub together so fast that they generate heat, and they may light off spontaneously, which would make the engine blow up, because you want it to be the piston, the rod, and the crank to be in the right angle, which we'll talk about rod ratio in a minute, in order for it to light off and combust to make the power you want. Higher compression ratio is good. Lower compression ratio is pretty sloppy and lazy, but it needs to be the amount of compression ratio you can run based on the fuel's tolerance of detonation. And if you're going to run 93 octane from the pump, you're going to have to stay near 10-to-1, 11-to-1. And there are bunches of guys on here that run 12-to-1 and say they can do it on pump gas. Everybody has a loose description of pump gas. Pump gas is something with an additive in it, some kind of gasoline at a different place than another place. But I know that if you're going to run 87 octane, you're going to need less than 10-to-1 compression ratio. And if you're going to run 12-to-1, you're going to need more 93 octane to get there. Another story. I know I keep saying that. Let's go to rod ratio. Rod ratio is the length of the rod divided by the stroke. So if you have a 8-inch rod and a 4-inch stroke, that's a 2-to-1 rod ratio. I wrote down a couple things that I have learned over my life was interesting. The small block Chevy, some of them came with a 5.7 rod length. Some of them came with a little bit longer rod length. I think the old 400 small block Chevy was a 4.55. Nope. 5.55 rod length. Y'all listen to me close now. I'm liable to say the wrong numbers. And then you take and put a big 3.75 stroke in that bad boy, you got a really short rod ratio. But the rod ratio numbers in our industry are usually between 1.5-to-1 and 2-to-1. And that is the length of the rod divided by the stroke tells you the rod ratio. And you want it to be, my opinion, is somewhere in between 1.5 and 2-to-1, which is about where really good race motors are real close to 1.7, 1.75. Last thing, and I know some of you know this is coming, the rod ratio is not number 4 in importance. It is probably number 37 in importance, but when I was thinking of ratios, that was one of the good ones I could think of that's very popular on the internet, is this term, rod ratio. Unimportant to me. The rod length is whatever's left after you get the stroke figured out, and you got the piston figured out, and you got room for the crank, and then the rod is whatever's left, and you get a rod ratio between 1.5, 2-to-1. If you go just under 1.5, it wears a little hard because the rod ratio is at a big angle and puts the piston against the cylinder wall at real high cylinder pressures. A little bit straighter up seems to last longer, and the real scientists back in the 50s and 60s and 70s try to turn it into something to do with cylinder head flow, which didn't really bear a lot of fruit. But when you were only could use stock heads and stock cast iron and stock OE aluminum heads, you had to do whatever you could do to try to find one more horsepower than the guy in the next stall. But nowadays, cylinder heads are so good, rod length is of small consequence, in George Bryce's opinion. Bore-stroke ratio is something a lot of people don't know about. But that is the bore versus the stroke. The bore, what we've learned over time, is the bore needs to be the biggest it can be so that we can get the most most flow and the most amount of valves. So if you have a real small bore, you can only put small valves in it, so that limits your horsepower capability, because the power is based on cubic inches and how much air and fuel we can trap in it and burn it, use it to turn the crank, and then get it out. And the bore-stroke ratio is important. One thing we've learned, pro stock cars are around 1.33 bore to stroke ratio. A pro stock S&S 160 is around 1.33. A pro stock Suzuki is around 1.33. And another one that's very interesting is the old 302 Chevy was a 4-inch bore, 3-inch stroke, was a 1.33. And there are some bigger numbers than 1.33, and most of the V8s and engines in the world have less than a 1.33 because there is no architecture or real estate for the bore. Am I jumping by this too fast? I'm sorry. Hey, Brian. Alberto or Jeff Shelton. You know, you just brought up something about Harley engines. Let me tell you about what I've learned on V8s with the overhead valve, one cam in the block, push rod engines. Is the longer the rod, the longer the push rods. And long push rods are wrong. So if you can get a short piston and a short rod and a short push rod, you have a stiffer architecture and geometry for the engine, because long push rods are like pole vaults and short push rods are really stiff. Intake to exhaust ratio. This was interesting based on some of the books and some of the heroes of our motor engine building industry were based most of their math and findings on small block Chevys and big block Chevys and some Chrysler Hemis and stuff. And what we found from the factory was 75 to 80% ratio between the intake size versus the exhaust size. Now with 4 valves, 5 valves, really big intakes, really small exhaust. Pro stock cars have gone to a bigger and bigger intake and gone smaller on the exhaust to make room for more intake. And their percentage between the intake and exhaust, I've seen everything from 65% of the valve size being a intake, and I've seen up to 85% of the valve size being on the intake. So there's several ratios here. There's what the intake flows divided by what the exhaust flows, or what the exhaust flows divided by the intake. There's the valve size. There is also, if you do the valve job and then you have the throat area inside the valve job, you have that area, the intake, versus that area of the exhaust, and it gives you a ratio. Ratios are really cool things that let us compare front to back, intake to exhaust, crank to rod, piston to bore, piston to stroke, bore stroke, all those things. It's really cool what the ratios are for. Nitrous to fuel ratio. This is another one that's very little known, because if you go to nitrous, you talk about you got to have 1,000 pounds in the bottle, you got to have 5.5 pounds of fuel pressure flowed through a 72 jet, and you got to be able to have whatever that size is, and you figure out the jet spread. Based on this bottle pressure, based on this fuel pressure, you get jet spread. Well, it's very, very inconsistent way to compare it, but when you get a really, really good flow bench, like they have, like Steve Johnson, I think he's Steve Johnson the second. There's Steve Johnson the 1, Steve Johnson the 2nd, Steve Johnson 3rd, Steve Johnson 4th, Stefan Johansson the 5th. I know about 5 Steve Johnsons. There's one that has induction solutions, and best I can tell, the way we always flowed our nitrous systems is we would weigh a bottle, fill it up, and we would hook it to our nozzles, and then we would take our gasoline and put a gallon in it and weigh it, and we would put it on scales, and we would turn the system on for 10 seconds. And in 10 seconds, we would weigh how much nitrous we used, and we weighed how much fuel we used, and it gave us a 7-to-1 nitrous fuel ratio. So that didn't care what the bottle pressure was. Yes, it did. It didn't care what the fuel pressure was. It didn't care what the jet size was. But if it was the amount of fuel you use versus the amount of nitrous you use, gives you a fuel to nitrous ratio that would help you be more consistent on your tunes, because some people want to know parts per million, pounds per million. I don't know all those different numbers they use, but in reality, it's the amount of nitrous oxide that we use compared to the amount of gasoline we burn to keep it jetted at an air-fuel ratio that's safe. Now, I hope we can get some good feedback on some of this stuff, because I am talking a little bit out of turn on some of it, and I tried to get 8 things done. But I want to tell you one more thing, cool thing about gear ratio. That's what goes in the rear end of the car or the chain and sprockets on the motorcycle. But the gear ratio is very important, because we can take an engine like a top fuel car, and they turn about 8,000 RPM going down the racetrack, and they run, say, 10,000, 11,000 horsepower, and at 8,000 RPM, I did a little math for you. Their rule, NHRA rule, best I know right now, you can call me out on this, but I think NHRA dictates that they have to run a 3.20 rear gear, which means that if the tire, the crankshaft is going 3.2 times more than the rear axle is. So the crankshaft's turning over 3 times, and the rear axle's turning over 1 time. I did 8,000 RPM divided by 60 seconds, gave me 133 revolutions per second, times Courtney or Ashley's 3.7 run made it. The crankshaft only turned 493 times from the start line to the finish line. So that's amazing to me, and I know some of you guys know this, but the crankshaft only rotated 493 times on her 370 run. And at a 3.2, that made the rear axle turn 154 times. Ran out of time. Speaking of times, I also wanted to tell you guys that all of this stuff is an opinion. And I know that we're brothers and sisters in hot rodding, engine design, motorsports, Harley Davidsons, fast engines. Some of you guys are just bored, want to be here, but I've been thankful to be doing this for my whole life. I started as a teenager, and here I am, 66, going on 67, Labor Day. Still racing, still enjoying high performance, still got a learning curve going like this. This is information I think I know based on all the years I've been doing it as a full-time job instead of just a hobby. And I realized that out of 100 people, 99 of them do it for a hobby, and the other 1% are lucky enough to kind of make a living out of it, or at least made their payments based on high performance in motorsports. I also know that the good Lord made us in His image. We're all perfect in His view, and we're all brothers and sisters in what we love here. And I want to say thank you. May God bless y'all. And I got a friend of mine on the other side of the earth sent me these socks, and I'll tell you what he told me. He said, "I'll see you next Tuesday." May God bless y'all.